So thanks to diagonalization, we can now do some serious stuff, some very amazing results. One of the results we can do is we can do functions of matrices. Okay, so for example, I will do a problem later, calculate exponential of m, where m is a matrix. Okay, you can actually do this. So how do we define a function of a matrix? Okay, let's remember that when you have scalars, f of x, you could always do like the Taylor expansion or the Maclaurin expansion. So this would be like an infinite polynomial with infinite powers, right? Up to infinity. So we can formally define that we can also apply functions to matrices, because we can calculate for a matrix M, we can do A0 times the identity matrix, which is the equivalent of the number 1, yeah, plus A1 times matrix M, plus A2 times matrix M squared, which we can calculate, and so on. We can calculate all the powers of M, and we can define the function in this way. So in principle, we can define functions for a matrix, and we can calculate a function of a matrix for any matrix. But in practice, it can get very difficult because we have to calculate m, m squared, m cubed, m to the 4, up to the maximum term in this expansion. And you know that for some functions, there are infinite amount of terms, okay? So it doesn't seem practical. However, if a matrix is diagonal, so f of a diagonal matrix, you can just apply A0 times I plus A1 times D plus A2 times D squared. But now this time, the powers of D are simply the elements of the diagonal raised to that power. Therefore, you can write this as 1 plus A11 plus, sorry. Let me assume, before I write that, let me assume that matrix D has D1, D2 up to Dn, okay? So it's a diagonal matrix with D1, D2, D3, and so on. So then, the first element of this matrix would be 1 plus A1 D1 plus A2 D1 squared plus dot dot dot. Yeah, that would be the first element. Then you will have zeros in the rest of the column. Then the next column would be 0, but in the diagonal, main diagonal, you would have 1 plus A1 D2 plus A2 D2 squared plus dot dot dot, right? You can apply that equation because it's very easy to do this calculation for a diagonal matrix. And in this way, you can do it for every diagonal element in D. And therefore, the end result is that your function applied to a diagonal matrix is simply the function applied to D1, then the function applied to D2, until the function applied to Dn, where the rest of the elements are 0. Okay? So we have kind of proved, I mean, it's not a very formal proof, I did it very hand-wavy, but you can see that there is some logic behind calculating the function of a diagonal matrix simply by calculating the function applied to each of the diagonal elements. Okay? So suddenly this becomes very easy to do, and therefore you can apply the function to any matrix as long as you can diagonalize it. Okay? So let's go straight into this example. Calculate the exponential of m for this matrix. Okay? Now, we know that matrix M is equal to A times D times A to the minus 1. Okay? And therefore we know that the exponential of M is going to be equal to A times the exponential of D times A to the minus 1. Okay? Because the transformation that corresponds to D, we are doing the exponential of that transformation. But this is in the diagonal basis. But in order to change it back into our basis, we just need to multiply by A and by A to the minus 1 at both sides. Okay? So therefore this suddenly becomes very easy. We notice that this matrix is the same as in the previous example. So let me copy the result from the previous example. Okay, I copied it here, the result from the previous example. So we know what D is and what A is. And therefore, e to the power m is simply this matrix 2, 1, 1, 2 times matrix D to the exponential of this matrix. So it's the exponential to the power 2, 0, 0, and exponential to the power 1/2. And then times 1/3, 2 minus 1 minus 1, 2. And this matrix multiplication, it's very easy for you to do it. So I'm not going to do the 3 multiplications because that would use up a lot of time, but you arrive at the following. Incredible, isn't it? So there was no mystery in calculating this. I just multiplied this matrix times this, and then whatever the result was, I multiplied it again by the final matrix. And you arrive at the exponential of this matrix. Quite incredible. I have to say that it's not very common to see functions of matrices in applications, okay? The most common application is raising a matrix to a power n. That is very common in applications. But I have very rarely seen something like an exponential of a matrix. But I'm just telling you that it can be done. So I hope you liked it. I mean, it's pretty incredible. It could well be a problem in an exam, but it would be a very difficult problem. So I agree with that. This would be something in part B because it requires so much understanding. It requires calculation of eigenvalues and eigenvectors in order to build these matrices. It requires understanding the change of the basis. It requires understanding the diagonal matrices. We can apply functions to them very easily. So there are so many pieces of the puzzle that I think this is a nice type of problem for a challenging question. Okay? So I hoped you enjoyed it. Thanks for watching.